Alright, so hello and hello, welcome, howdy. Today we're going to look at another question, another problem. Let's get it going. Starting to consider that I should not be messing around with, basically starting to consider that perhaps I've been wasting a lot of time. And I've been frustrated lately. Frustrated with some things. Yeah. That's okay. It's alright. I'm going to try to keep, so I think the plan for me is going to be to pretty much solve all the problems on the site. Do that, right? Probably get a job. It's just, nothing job, basically. Just to pay the bills. And then once I've done that, once I finish all the problems on the site, I guess from there I have some choices of what to do. There were some places I've been interviewing with, but the more I think about it, the more I'm like, it's frustrating. Working for somebody else maybe is just not for me. I don't know. Possibly as a developer, as just a regular old employee, just moves boxes from here to there, like whatever. I don't care about that. But when it comes to like engineering, I've noticed there's a lot of I don't even know what to say about it. I'll just say working for someone else as a software developer just seems not the best approach. But anyway, I won't get into all of that. So, given strings S1, S2, S3, find whether S3 is formed by an interleaving of S1 and S2. Interleaving of two strings S and T is a configuration where they are divided into non-empty substrings, such that S is concatenated in first character, second character, all the way to S sub n. T is concatenation of T sub 1 to T sub m. N minus m, the size of n minus m is less than or equal to 1, the absolute difference between the two sizes. The interleaving is S1 plus T1, S2 plus T2, S3 plus T3, or T1 plus S1, T2 plus S2, So, yeah, basically you pick one character in one string and then the next character in the other string, and you do that to concatenate the strings. And so note A plus B is concatenation of strings A and B. S1 is AA, B, C, C. 2 is D, B, B, C, A. 3 is AA, D, B, B, C, B, C, A, C. Output is true. This is not a very, I got a lot of outputs, but I don't think this is described particularly well. Non-empty substrings. Oh, okay, well maybe, are they subsequences or just substrings? Because this is a little bit confusing, right? This interleaving, the description of the interleaving here is not exactly what I was expecting. It looks like you can take as many characters from one string as you'd like, and then switch to take as many characters as the other string as you'd like, and then switch again. Yeah, that's interesting. So, might need to do some dynamic programming, I guess, here. A, B, C, C, D, B, B, C, A, D, B, B, A, C, C, C is false. So this one is true, this one is false. Empty strings are true. The strings themselves are only size 100, and the target string is 200. So I think you need to do something kind of fancy here. Solve it using only O of S2.length additional memory space. I don't know. Well, interesting. So what you could do is, I guess another way of thinking about this is you can intersperse the second string into the first string. Yeah, I don't know why this even matters at this point. This check. Fortunately, on LeetCode, you can run test cases to see. This is not one that I'm familiar with at all. This might take some time. You can run some test cases to see like what they mean. Let's actually do that. So like I just want to check. Do like A, D, and then we just A, D, A. 1, 2, 3, 4. And let's see, what do we get in the second test case? Just because I need some clarification on what they mean. What they're expecting. A few things to say about this. I don't really have a solution. So, okay, so the second one is true. Now, let's say you remove a character. Right, so I don't know what they're talking about with this, and absolute difference is less than or equal to 1. I don't know what they're referring to at all. So false. So it looks like you do need to use all of the characters from A and B. So part of the issue here is that you could do something like you read on the third character. You basically can treat these like stacks, and just read. You see AA matches AA, D matches D, BBC. Now what's interesting here is that BBC actually matches both here and here. So you can take this B, or you could take this B. And see that's where things get kind of dicey. That's where you might want to use like some dynamic programming, I suppose, where you can choose this B, but then you realize that if you use this B, you say B, and then you take this C. Just so happens to be a C here, but if this was like a D, you would need to actually take this BBC instead of this one. So you can run into situations where I'm just going to sit for a moment because I'm realizing now that I may need to use some sort of fancier algorithmic approach here, like a recursive approach or dynamic approach or something that's not as simple as sort of other approaches. But yeah, in those situations, then you need to make a choice, and you kind of branch into two different, I guess, two different scenarios, I suppose. Yeah, if there's no choice though, then obviously you would return. So you can do. The tricky thing here though is we can memoize this. Just thinking about that too. I think if there's another way to do this, it's better. Because the problem you could end up with is we can use recursion and memoization. I think we could solve this at least quadratic time. Part of the issue is that if we recurse and we say something like, hey, let's hold on a second here. If we recurse and say something like, you can, if both the characters are the same, then you have a choice. You can recurse on the left side and recurse on the right side. Or not left and right, but recurse on the first string, recurse on the second string, taking characters. You can do that. That's all well and good. and you can memoize that recursion, so it's not exponential time. But I guess that's the problem, is that if you recurse in that way, it could take exponential time, because you can run into that sort of fork in the road multiple times. The tricky thing there, so there's got to be a way to optimize that, though. I think that's the thing I'm wondering, and they're actually saying you can do this in a way that doesn't use that much extra memory. So you can use quite a bit more memory by you can use quadratic memory. Oh, I see. Actually, I see how you could end up doing this in linear memory. Oh, I understand now. Yeah, this is it's very similar to some other problems so if you use a dynamic programming solution, I think I get it. I think I got it. This is not as hard as it looks. Let's do this. How are we doing on time? 11 minutes. All right. So let's try to solve it first, and then from there we'll try to solve it first, and then from there we're going to optimize it, I think. Let's do it that way. Yeah, because there's only 100 characters that we're using, so it shouldn't be too bad. But yeah, so if we go something like this, let's see, we can do, we actually want to use something kind of special here. And we'll use tuples as well. Okay. So this is going to look like the following. So we're going to have auto. It's going to call it DFS, even though it's only a. I'm going to say standard unordered map. Int memo. We're actually going to also use a struct here for the hash, I want to say, custom hash. And that's going to take an operator. And we're going to have, this is going to return a size t. And it's going to be a const. It's also going to be const standard tuple int reference x. Excuse me, I did that wrong. All right, so for custom hash, and we're going to return it's gonna be something like this: hash 1 standard hash of int. Call that on x. Get 0 of x. Hash the second one, return h1, or XORed with h1 minus h2 minus 1. Something simple like that. I think that's what you can do for a custom hash opera function. Let me just check what the documentation says about this. Let's see. All right, 14 minutes in. Size the operator const no except. We missed the no except. That's the only part. And you bit shift instead of subtract 1. So I want to bit shift. Okay, that's fine. Fair enough. So we're custom hash or memo. And we're going to say constant x, or actually I, constant j, DFS, or we're going to say DFS. F. And what we want to do is go to memoize in each case. Actually, I think you just return. I think that's it. Just return. DFS, DFS, you have I and J, and there's a final value K. And we say something like the following. So 0, 0, 0. And we have a base case. Say if, base cases. Say if, so we have a couple of things. If K is greater than or equal to, we can actually say N is going to be S1 size plus S2 size to N. Return true. And it's actually, we have to use I and K, yeah, okay. If, let's do something like the following. Okay, we can do this, that's fine. I think it's just say like size 1, size 2, something like that. Okay. So if we're not in this case, actually, just thinking here. Yeah, so this should still be false at the bottom. Hold on a second here. This wrong too. I think you need custom hash. Something like this. Oh. Forget these things from time to time. I have to come back to these things. can also just go ahead and so we won't be able to yeah, so it's got to be equal, otherwise you return false. We can terminate early then. All right, the next thing would be size 1, size 2, our base cases, we have our DFS. Okay, so what we're looking for is now the way this is going to work is I, J, and K. Yeah, we don't need to calculate I and J every time, or calculate K every time. So we have base cases, we have our tuple. If K is past the end, return true. If we're not, then we say if either of these are past the end, then return false. How are we doing on time? 22 minutes, all right, not great. Really, if either of these are past the end. Now, presumably if they're, well, that's actually not true. It could be, yeah, so actually, you do the other way around. If I is greater than or equal to size 1, then really what you want is the end of the second string. So it would be string, I really need all of these, S1, S2, and S3. That's a tricky thing as well. It would be S3.substring from J to the end. If that's equal to, so bool ret, or just, yeah, ret's fine. If that's equal to the rest of the other substring from, excuse me, from K to the end, is equal from J to the end, and then return ret, right, just like so. Same thing, although sort of the other direction. If you don't have any more characters to interleave, then you would say, if this is S1I, and then what you're going to do is say recurse on F. So if S3, so we're going to say characters X is going to be S1 of I, Y is S2 of J, and Z is S3 of K. And we're going to say if X equals Z and Y equals C, and then we're going to say bool ret equals the left and the right, left or right, so F on the left side or F of the right side, and we're going to say memo of key equals ret, return ret. Otherwise, X equals Z. Do a similar thing. So the logic here is a little bit involved. And I suppose in all cases we could return ret at the bottom. So having that line everywhere here. And now if neither of these are neither of these are equal. So this is, both of them are equal. That might not be true. It could just be x is equal. It could be just that y is equal. But if neither of them equal, or if they're both equal, then we have to go through both cases. If one is equal, then we go through one case. And finally, if neither of them are equal, we just set ret to false. So I would say we could set ret, and we can say memo of key is equal to ret. That can be here as well. And you would say boolean ret is initially false. And so you don't need else, really. And so these all can be changed. So simplified. So ret is going to be I, J, K, F. And again, I, J, K, F. And then here again, I, J, K, F. And same thing here. And now we have one more issue, and that is all of these are k plus 1 no matter what. It's always k plus 1. How are we doing on time is a question to ask. 27 minutes, okay. Not ideal, but not too bad either. And so we say for this would be the recursion on the left side and recursion on the right side. The left side, if x equals z, we do plus 1 here. On the other side, we do j plus 1. And we have both of those possibilities. And then this is if it's x is equal to z, we increment I, otherwise we increment j. And in this case here, we just return. If we, on this one, if we, there we go, nice. And this one we just return if we're in none of these cases, and then terminate early. So that's great. So all right, I don't know. Let's try some other cases here. DF1, 2, 3, 4, DFF, I guess it would be something like this. I don't know. Let's try some other examples they have here. Can we use the test cases? Yeah, okay. Excuse me. See if we miss anything. Ooh. Which one is that? Oh. Each test case has 3 strings. All right, it's probably pretty good. What test case could we be missing? I mean, I don't know. A couple things before we hit submit, right? So this is like discipline, an issue of discipline. How can I be totally confident that this is correct before I hit submit? Well, quite frankly, I'm not totally confident. I'm not. don't actually have a solid way. I mean, I guess I just have to trust that my reasoning, trust that I got all the tricky cases. I don't think there are too many tricky cases with this, actually. I don't know. Let's go for it. Probably I would just want to come up with a bunch of test cases and try it before I submit. Definitely nervous though. TLE. What? Oh, come on. Oh, well, I was wrong. Isn't this exactly the test case that I was supposed to handle that would be tricky and... How? What do you mean it TLEs? Isn't this exactly why I think the tricky part is you need to return here in between. I think that's why. Yeah. The problem is when you call this, you still end up you're not memorizing. You're memorizing down here. You're not memorizing up here. So you have to memorize actually after each case. Yeah. So you have to kind of break this up. I think that's the issue. Am I crazy? I don't know. Maybe I'm... You don't actually have to put that there, though. Maybe this is why? I don't know. You need to terminate early. Oh! No. Well, but... I totally forgot. Just not using the... Okay. Of course. No, this wasn't why. Just looking at it like, wait a minute, what's wrong? What's the problem? I'm so bad at this, man. I always miss something. There's always some subtle thing I miss. I don't even know how do you remember to catch these things? How do you remember to catch these things? These mistakes. Ah, it's so silly. I feel dumb. I did such a good job too, up to that point. I was doing so well. It's always something, some subtle thing that I forget. I have to actually remember to use the memoized. The memoized array, or memoized, use that memory. Oh man, I'm so disappointed. I really am. I'm so disappointed. This was such a gimme. This is such an easy question to do this way. Yeah. How do you remember that? I guess you just run your check over your base cases. Remember to check. Did you memorize? It's funny. I did all the I added all the memorization here. I did all that cleanup, but I just forgot to. To do the check here. And I even thought about it too. I was like, what could I be missing here? There aren't too many tricky test cases here. It's kind of straightforward. Now, what is interesting about this problem, though, is that a couple things. You're using quadratic memory to do this, right? Memory that's potentially quadratic memory. And the problem with that is that's a lot of extra memory to use. It's a linear time solution, or no, it's not linear. Excuse me, it's quadratic in it's actually quadratic time algorithm and a quadratic memory algorithm. But what's being asked, what's being suggested is that there's a way to do this with only O of the second string length additional memory space. Which you could use the minimum of S1 and S2, right? You could just swap the two strings, so we are only using the smaller strings memory. So you could use less memory too if you wanted to. But the problem with that is you can use less memory if you wanted to, but the problem with that is it's kind of tricky. So basically what you're going to want to look to do is somehow not use I want to say something like you can, it's a way to approach this that doesn't require that much memory. It has something to do with, like, if you could imagine that this creates a tree of if you can imagine that these function calls create like a tree of subcalls, right? What you can do is say we only need the memory for the previous level of calls. Like, we don't actually need the memory for all the way up the tree. So this is sort of how you can optimize the memory. So you'd have multiple. So it's kind of like this: the function calls. Even though it's in two-dimensional space, there is sort of always this previous layer, and the ij. They so like each ij pair represents some value here in this sort of like an array, I guess. And you don't actually need that much memory at each position, each step to calculate the next one. You only need the previous one. That's kind of what's going on here. Or I guess you go backwards. Really, is you start. You can reverse the algorithm. You can go bottom up. I think that's really the way to describe it. Is you go bottom up. And from here you can then calculate, the parents, but the parents of each of these nodes. It's kind of what's happening. If you think about this, you would say, like, these are recursively computing sort of the next, like, it's sort of generating the next level, and then what happens is once those values are determined, then it rolls back up and the stack gets unrolled. So you sort of create a call stack as you recurse down, and then you sort of roll that stack back up once you return from all of these functions, these function calls. And what you can do is you can actually start at the bottom if you wanted to, and then go back up and then go up. Although I don't actually know how to do that. That's the thing. It's really tricky. But that would be a dynamic program. So you can convert this to a dynamic programming. This is technically it's a memoization approach, but you can convert this to a dynamic programming solution, and actually start from sort of the bottom layer in sort of in memory of like where all those points stop, and then go up. I think something like that. Actually, I don't know. I'm thinking about it. I don't know if that makes sense. Because if you knew the answers at the bottom already, then you'd be done. You wouldn't even need to the algorithm would be constant time. So that's not true what I just said. I don't know. What I just said doesn't make a lot of sense. I want to say there's a way to do this using dynamic programming that way to do this using dynamic programming that's doesn't use as much memory. Technically this is dynamic programming, but like this is like the most intuitive, simplest approach kind of a thing. It's like very not brute force, but like very straightforward kind of approach. But obviously uses quite a bit of memory potentially. O of sort of m times n, where m and n are the sizes of the two arrays, smaller arrays. But you can do, how can you do this? Let me sit for a while and ponder this. Oh boy, my body. Let's think about this for some time. Let's ponder this for some time. Yes, this works. That's fine. But how do you reduce the memory usage for this? There is a way to do that. There is a way to reduce the memory usage. But how do we do that? Gotta think about this here. Well, I could just go look at the discussion and see what they say. But there's kind of a generalized approach to doing this, though. It would be something like, oh, no, yes, no, I'm right, actually, about this. I take it back. Well, yeah, I'm sorry. I take it back. No, I was right. I was right the first time. Yes, you can go to the bottom. Yes, you can unroll the. No, I was right. I had the right idea the first time. Yeah, no, exactly correct. No, that's fine. That's fine. You can go backwards. That's fine. You can go backwards from the bottom. But the checks would happen at the there would be additional checks at the root nodes. That's the issue. In other words, yeah, no, I had it right the first time. These checks that happen, you would also perform those checks when you're going up instead of going top down, you can go bottom up, and these checks happen from the top down. That's the key. Yeah. That's actually I was right the first time. That's how you could do this with less memory, is you could perform the checks going up. And actually, I think ultimately the amount of memory this uses. I think it's the problem with this approach is because really the issue is what I'm doing now gives you the memory of the entire tree, which is quadratic. But you don't need the memory of the entire tree. You only need memory of the layer that you're operating on. That's the issue. Yeah, that's the problem. So you can actually dump some of the memory. So that's the key to it. And then if we look in the discussion, you'll see, I'm not going to go through that. I mean, you could go through that. It takes a lot of time. Actually, it takes a while to kind of like figure out exactly how to go up from the bottom of the tree. I guess it's not that complicated. You're kind of just inverting these operations to go backwards. You can do that. It could take some time. So I won't do that. But we can look at the discussion. It'll show us how to do this. BFS. Looks like a tiny DFS. DFS, BFS. Yeah, I guess BFS doesn't use as much memory too. You could do BFS as well. If you could do DFS, you could do BFS. Sure, let's do. Yeah, that's exactly what I was saying. You have to, those conditions, you have to sort of roll them up and go backwards. That's how you do the DFS, or not the DFS, this is dynamic DP, rather, it's not DFS, or BFS. Oh, that's interesting. This can be 0 milliseconds. Vector is really slow. Oh, okay. So you could do 0 milliseconds by not using a vector. And then they'll, yeah. Yeah, this is the DP approach that would be, and this is very efficient because you have, DP approach is more efficient because you can use, instead of using a vector, uses less memory as well. If you could use DFS, you could also do BFS as that as well. How old is this? 2018. Interesting. Oh, I didn't really think about I didn't hash I wrote a hash function, but I didn't really write an equals function for my tuples. Whoops. Oh, that's interesting. Oh, no cursing. But how did we get, how did we get Q.00 pop push visited down right? Well, if you could DFS, you could also BFS, but what kind of BFS do they have here? The cell on the board. Start from top left corner and try to move right or down. AAB, ABC, AA, BCB. The board looks like this. So you have A, so there's ABC. Oh, I see. So you have ABC from left to right, and then you have AAB top to bottom. Yeah. These are all the possible choices you can make. And the DFS tries to find. Actually, really, DFS is just trying to go to the bottom, either here or here. These two positions, and each time you can only take a path that has one of these, whatever character you're looking at. So BFS is A or A and A. These two possible positions, and then from those positions you can only do another A, do another A. Oh, I see. Yeah. So you can't do B, but you can do A. You can do another A, right? So you end up with this spot. That's interesting. You can do A and A, but you can't do A and B. You could do also A and A if you. Yes, you have to make sure you don't revisit, right? And so you're here and here, and then you can. It's interesting that the DFS doesn't require any. Doesn't require. Oh no, it does. That's the memoization. The DFS does already. Yeah, no, that's exactly. Oh, that's why. You can write the DFS too, but the tricky part is I think the BFS also has potentially. No, the BFS is also not. The memory to the BFS is also quadratic. Yeah. Both the BFS and the DFS are quadratic time. Not quadratic, but proportional to the Cartesian product in memory. Yeah. Yeah, this is interesting. This is not, it's actually, yeah, they're both NM complexity, but also this one is, the DP algorithm is the optimal, because the DP algorithm allows you to optimize the memory. The BFS, the DFS are suboptimal because they don't allow you to easily optimize the memory, which also makes it actually faster, the DP, because of, the DP is also faster because the way that you allocate the memory using either a vector or something on the or an array on the heap or an unordered set or unordered map, right? There's a few different ways to do it. Yeah, from top down to bottom up, 2D to 1D space is the way. This is the way. This is the way. I recommend this way. 3 lines DP explained. Brother! Dude, this is wild. What? Oh, you cache. Yeah. Whoa. That's pretty wild. Whoa. No. Can be reduced to M plus N. That's pretty good. That's pretty good. Yeah, cache memoizes the function. LRU cache is great in Python. In Python. Alright, anyway. Alright, that's probably enough time we spent on this. Yeah, basically all the problems that you can solve are like this. Pretty much all the problems on LeetCode, I don't want to say all of them, but a lot of the problems on LeetCode are like this. I'm disappointed that I didn't solve it correctly. I'm disappointed. I'm disappointed. Because I forgot to memoize. Yeah. So this is kind of a classic thing you can do. Maybe I should for the problems like this. Maybe I should go for the DP solutions first instead of the like basic memoize problem. But this is like a very easy, straightforward way to solve problems of this nature, like really quickly. You gotta kind of recognize them, but you can. This is like a generalized approach that just like you can always solve them like really quickly. But the tricky part is then converting this from a top-down recursion, memoized recursion, to bottom-up DP, where you can use optimize the memory. Because if you can optimize the memory, then you could also optimize how you allocate that memory, and then you can make it faster, and then you get 100% every time. Yeah, so that's the trick for these questions. But for now, I'm still kind of practicing just being able to write this very quickly. And correctly, and doing it this way, and then I could start practicing like writing the DP solution that's optimal. That's like super optimal, or is just optimal. Yeah, optimal DP solution. But the algorithm itself, that you really can't do better than quadratic time. Like a lot of the dynamic programming solutions that are out there, or questions they have out there, really it's if not extraordinarily difficult, if not impossible, to go do better than like some polynomial in terms of the number of, some polynomial in terms of the number of variables, or some product of the sizes of the variables. The product of the size of the inputs. Yeah. So like in this case is O of n times m, where n is the size of the first string and m is the size of the second string. Like pretty much all of the dynamic programming questions that they can ask you here are always going to have that sort of form where the optimal solution is always kind of looks like that. So yeah, pretty nifty, pretty neat. Again, disappointed that I made a mistake. I mean, I always make mistakes, man. I'm always messing this up. I was so close. I always forget. But anyway, all right. That's enough for this question. Thank you for watching. I appreciate it. I will talk to you soon. Have a good rest of your day. What I want to say, yeah, I don't know how much more programming we're gonna do today. A friend of mine, I'm actually helping to teach him how to program. So that might be a while. We spent all day yesterday, so we'll probably spend a lot of today as well. So yeah, thank you for watching. Talk to you soon, and take care. Take care.